All right, starting chapter 5.1, which is about antiderivatives. It's all the fun of derivatives, but backwards. So sometimes we have the rate of change formula, but we don't have the original function that it must have come from by taking the derivative. And we want to get a formula for the original function. We've already done some of this in by Euler's method, or solving differential equations. That gives us not a formula, but a set of numbers, which is often very good and maybe all that we need. But sometimes we also need a formula. So let's just take a quick reminder. If f of x equals x squared, what is f prime? Hopefully you said 2x. So then if some other function g prime of x equals 2x, what would you guess that g must have been to give me g prime equals 2x? Well, since I just gave you this big hint, you're probably thinking x squared. Seems like a reasonable guess. It certainly works. Let's try another scenario. If we say f of x equals 1/7 x to the 7, then f prime is what? Go ahead and do that in your head. So you probably got 1/7 times 7x to the 6th. Remember, we don't need the product rule or quotient rule there because 1/7 is a constant vertical multiplier. And obviously we can cancel the 7's there, and we get just x to the 6th, right? So if g prime of x was equal to x to the 6th, you'd say g of x was what? Well, you probably noticed we just kind of got that answer, so we'd say it's 1/7 x to the 7th, right? Seems plausible. I'm going to put a question mark there. It certainly works. If I started with 1/7 x to the 7th and took the derivative, I would get x to the 6th. So let's make it a little harder. What if g prime of x was equal to x to the 5th? Then what would you say g of x was? Probably noticed just the pattern here. So the 6, when we went backwards with the power rule, became a 7. So we'd probably get x to the 6th there, and then we'd need a 1/6 there. So when we took the derivative, the 1/6 was waiting in ambush for the 6 to come down to cancel and just give us x to the 5th. What about if g prime of x was equal to cosine x? You'd say g of x seems reasonable that it would be what? What do I have to take the derivative of to get cosine? Well, a reasonable answer would be sine of x. Notice I'm putting a question mark here because there's more to that story, but sine does work. It gives you a derivative of cosine. And then the more confusing one, if g prime was equal to sine, what is g of x equal to? What do I have to take the derivative of to get sine? You might say, well, cosine, but derivative of cosine is negative sine. I need a negative sitting there to cancel the negative I'm going to get by taking the derivative of cosine, so I get a positive sine. So those are some basic antiderivatives so far. Let's talk about some antiderivative notation. So an antiderivative is a function whose rate of change is the function that we already know. Whose rate of change function is the function we've been given, or that you could say the function we're starting with. Some people would say, what's the original function if I know the derivative? Some people would say, what's the parent function if I know the derivative? In some countries, I think they tend to call it the primitive function. That's fine too. How do we write this? So if I have f prime, we would say its antiderivative is, what's a common name for the antiderivative of f prime, do you think? Well, just f, right? And then, more complicated, if I have f double prime, its antiderivative is, what's a good name for the antiderivative of f double prime? The function that when you take the prime of it, you get f double prime. So probably f prime, right? So here's the puzzle. If the function I have is called f, so you might have noticed here, I kind of take a prime away to get this. I take a prime away to get this. If I don't have a prime here, how can I take away a prime? Suppose I could write a prime in a different color, or write it on a different side of f or something. But the convention is we call it big F, or capital F, or uppercase F, or something. So little f is the rate of change of capital F. So little f is the rate of change of capital F. Or we could say, if we want to relate big F and capital F, where do I put a prime to make these two things equal? So I'd say the derivative of big F is little f. So now we have to be careful about when we use uppercase and when we use lowercase, because it makes a big difference. When we use Desmos, you can do capital F and you can do lowercase f, and Desmos will see them as different functions because the people who programmed it know that it's a big distinction between big F and little f. Let's look at another way of talking about antiderivative notation. So if I have, let's go crazy, f quadruple prime of x, we know that you can write that as f super 4. And the 4 in parentheses doesn't mean raise this to the fourth, it means take the fourth derivative. And we said f triple prime, you could write that as f super 3. F double prime, you could write that as f super 2. F prime, you could write that as f super 1. And I think we said last time we talked about superscript notation here, little f all by itself, you could say, well, that's the 0th derivative. And then what goes in this pattern? Well, 4, 3, 2, 1, 0, blast off? Well, the next number that's handy is -1, which would be the negative first derivative of f. And what's the name for that? That's capital F. So you can actually write it this way. We don't usually write it this way. And also, this does not mean inverse function. F super -1 sometimes means inverse function, sometimes means 1 over f, just depending on the context. But f super 1 in parentheses would mean the first antiderivative of big F.